This video will continue our discussion of line integrals in conservative vector fields. So they want us to find work, which is defined like this. We've done that in past sections, that we know that that is equal to work. But if I can show it's conservative, I can use the method that we just talked through when giving a potential function. I just got to find my potential function, which we've done several examples of, right? If it's conservative. So we need to check m n. The partial of n with respect to x is equal to 2. That's also the partial of m with respect to y. You can take a look there. So that means that f is conservative. All right, I'm going to work through this method. It's the same like layout every time. So if that's the case and it's conservative, then there's a potential function phi that's equal to my vector field, which means the vector field can be redefined as the partial of phi with respect to x, partial of phi with respect to y. Right, so that also, if we look at our vector field right above, that's equal to m and n. We're going to use that fact to undo the problem, just like we have. So the phi of xy is equal to the integral of phi with respect to x dx. Well, phi with respect to x is just m dx. And then now this allows me to work an integral out because I have an m, 2y plus 1 dx. Okay, that's going to be equal to 2xy plus x. And then just like before, we have h of y. Because we did it with respect to x, that means there could be a y there still. All right, so we have a phi. I like to rewrite it here. 2xy plus x plus h of y. I know I write a lot of so's, and you're like, why do you do that? I think it comes from proofwriting, starting my word with a English word. I just don't care about being tacked and using more. Usually you switch your words up, but I don't really care because we just care about the math. That's just a habit of mine. Anyway, so we're going to take the partial of phi with respect to y. And I have phi right above here. This is going to be 2x. The x is a constant, so it's gone. And I get h prime of y. And I'm going to set this equal to, because I know phi prime of y is equal to n. So I'm going to set it equal to n. N in this case is 2x plus 3. What that means for us, so h prime of y is equal to 3. And then I'm going to be a little informal here. I can do that integral without thinking. I think you can too. 3y plus c then. So I'm going to write thus this time. So phi of xy is equal to 2xy plus x plus 3y plus c. Now the problems in the past would be done right there. But what's really nice about this method is I know that the line integral over c of f dotted with dr, that's work. Right? The work is going to be equal to phi, which I have, and then we have points that they gave us. They said start here from a to b, and we just do b minus a. So I'm going to plug in negative 1, 1, minus phi of, I think it was 0, 0. Yes. Right? Plugging these in, we have, okay, I'm just plugging them into x and y above. You can do that calculation with me. I get negative 2. Just plugging these in. I got a minus 1, a plus 3, and then I'm going to write c this time, and I probably won't ever write c again. You'll see what happens with it. We then have to plug 0 in for x's and y's, so we get 0 plus c. This ends up being a 0. The c's go away as well. I'm never going to write the c again because if you think about it, we're always going to have a c minus c. This is a definite integral. They go away about like they did in Calc 1. So the work done here is 0. There we go. So that's actually how we use this method given a conservative vector field. We can work backwards, find our potential function, and then just plug our values in as long as it's conservative.